Okay, most cases we think of two different movements. We think of voltage, and we want to call this amperage, but that's not entirely correct. This is forward EMF, and this is reverse. Okay, and as it turns out, the bottom one, or the reverse EMF, is basically your amperage. With the amperage, your potential, which would be your forward EMF, and this is what's important. The potential is what the working voltage that you have that can, it's trying to go back to background. And the process of getting it back to the earth and our air background, it's going to go at a certain rate, and the avenue which it goes there, or allows it to move to the earth ground, say, is what determines the amperage. Amperage does not enter into it until you start draining the potential.
Okay. Now, how does that relate to what you're doing? Is that what's really pulling all the energy out? Or?
Well, what it tells you is the spin on the top one here, the voltage is going to be, the electrons are going to be spinning. Let's see, let me get this right. Let's see, it's got to go this, on the amperage down here, the electron spin has to be counterclockwise, and on the voltage, the electron is spinning clockwise.
Okay.
So basically what happens is, when you're pumping the electrons, you're alternating between the clockwise and counterclockwise spin, and you're getting electricity out of the clockwise spin, and the counterclockwise is going to be your reverse EMF, or they really haven't named it properly. It should have a name all of its own. It's not really amperage, even though that's what it is considered to be by some.
Okay.
It only becomes amperage when it's trying to return to ambient or background or earth ground or air ground.
I got you. Could you do like a rough sketch of your device and how the electrons travel through it, what's happening along the way?
Okay. Okay, you have a little module. This would be your power module, or it might be a neon tube transformer. Okay, and it's got the alternating current stuff coming out. We've got a 12 volt one here, so we've got a 12 volt battery here, and we've got a high voltage module.
Like, is that like your neon light?
Yeah, if you'll hand me, there's one on the table there.
There you go.
Okay, this is one looking at you. The black and red are the 12 volt wires. The two red ones are the alternating current wires. Okay, none of the 12 volt electricity that goes in there is coming out at those the two red wires. It's a Tesla coil, or miniature solid state Tesla device, and 3,000 volts is coming out, and only 12 volts went in at very low amperage, and amperage does not enter into the picture until you earth ground it. When you earth ground it, well, then the flow rate trying to unload that 3,000 volts to the earth ground will become, that's your amperage.
So you could actually use that on this
actually, I'm going to show you how to make a simple one.
Okay, great.
Most of the things that are in my devices, which I demonstrate, were put there because people expect to see them, not because they need to be there.
Okay.
Okay, so this device, which I had turned upside down, okay, is the high voltage module here. So we come out and we need a L1 coil here. It's going to be our L1, or input coil, and we're going to run this, since this is alternating current, it's neither plus or minus. It's going to be, what it's going to be doing is coming over here and into here and coming back, just like that. Okay. So we've got our high voltage device, and we've got an L1 coil, and it's all working just fine. At this point, it's running at 35,000 cycles per second. Okay, and we don't, the method I'm teaching you here, you don't have to know about tuning. The fact that the length of the wires that go on this coil here are basically irrelevant, because it's being pumped by the high voltage device here, and that's going to set the frequency. The length of the wires are not going to have anything to do with it. So you don't have to know how to tune it to do this. Okay, the next thing is that we're going to have an L2 coil here, and it's going to have coils on it, and it's going to be out, and this is going to be your minus, and this is going to be your plus down here at the bottom, and electricity or electrical field always moves from the highest concentration to the lowest. But in this case, what's happening is each coil there has a capacitance and inductive characteristic. So it's magnifying. For example, say that this is 3,000 volts here, and we have 10 turns here. So this is volts, and we have 10 turns. Okay, we divide 10 into 3,000, and that means that each turn is going to equal 300 volts. So each turn on a L2 coil here, each turn on there will have 300 volts on it. So if you have 30 turns, you've got 300 times 30, which would be, let's say, 300 times 30. Okay, and that's going to be 0, 0, 0, 9. So you're going to have 9,000 volts on your L2 coil. Okay, and it's going to do that irregardless of the amount of turns or the frequency or whatever. What we're doing by forcing the 35,000 cycles per second onto this first coil, we're forcing that second coil to duplicate the same thing, as long as it's an even division of or multiple of the wire length in the first coil. Okay. So we've got, at this point, we've got 9,000 volts out, and we probably will want to put a spark gap of some sort in here so that we can, and this goes to your earth ground. Okay, the center part of the spark gap will go to earth ground. Okay, and this is going to limit the voltage so that it's within the range which you can handle it with whatever device you're going to load this with. So you can go directly from this into your transformer out here, and it'll be an isolation transformer. And at this point, what you have to do, since you've got a frequency which the isolation transformer cannot use, you have to correct the frequency. So in order to correct the frequency, you put a resistor across the two poles there. In order to determine what resistor size you use, you go to either the American Radio Relay League chart showing capacitance and resistance and other types of things, which will tell you what approximate frequency you'll end up with. Now, in the case of American Radio Relay League, you're going to be off the end of the chart, and you're going to have to take a little piece of paper and make the grid and extend the chart over about an inch or so and about an inch or so down in order to get, say, 60 cycles or 120 or whatever it is you want. But you can do that real easy.
Okay.
So anyhow, we've got through our 12 volts, and none of the electrons from the 12-volt battery have left the high voltage module. The high voltage module has excited electrons in a separate, just like your transformer here, where you have the two sides are separated from each other, so that none of the electricity on this side actually goes through the system. What it does through induction, it excites the coil on the other side, and your electricity over here is coming from the earth grounding, and your load is going to be in between the earth grounding and the other pole of that transformer. And you're going to have to also put some sort of voltage control on this thing here, and that will be a varactor, V-A-R-A-C-T-E-R. And what that is, like on your computer where you have a voltage control thing that keeps the spikes from coming in, it looks like a little capacitor, but it's not.
Okay.
But it basically will limit the voltage to some level which is okay for the device that you're trying to run. Now, what I have shown you here, you don't have to know how to tune it. That takes care of itself for you, and you have to make only one correction in the frequency, and any coil and resistor or any coil and capacitor or any combination of those will give you a particular frequency. Now, Radio Shack has a book on electronic tables and such, and you can use the charts in it.
Okay. Is this the smaller simplified version?
No, there's some solid state versions of this where all of this is thrown out, but I'm not at liberty to talk about them just now.
But this can give somebody an idea that you don't actually have to
You don't have to know what you're doing at all.
Now, will this draw energy out the same way as your other
No,
ones?
it works. It's the same principle. All it is spinning the electrons, and you have these isolation deals where the electrons that are active from your battery here are disturbing the electrons which are on the high voltage side here, which are going forward, and your L1 and disturbing the electrons in your L2. None of the electrons from L1 are transferred to L2, only the inductance. And it has disturbed electrons here, which go forward, and again, it excites the inside of the output transformer, isolation transformer, which in turn excites the other side, which is grounded into the earth ground and to the load. And at that point, the electrons that you're having are coming out of the earth grounding. They're not coming from the battery or anywhere else.
So that's it. That's the trick.
Yeah, it's and the whole thing, regardless of what you do, the same system holds up for every device that you're doing, including the more complicated ones, which people are having difficulty with.
Okay. So is this a simplified version that everyone has been trying to build?
Yeah, this is the one for those that can't.
Now, is there a trick to tuning it to an earth frequency so that it makes energy?
Well, you can tune it to any frequency you want, but the earth frequencies are so low that they're not very useful.
So you're not tuning it to the earth?
No, it's the only thing it's tuned to. It's grounded. The earth grounding is what matters. Somewhere in the system, it has to unload back to an earth grounding in order to establish ambient. That's just like water from the ocean. It comes up in the clouds and falls in the lake and has to work its way back to the ocean.
Would a device like this work in an airplane?
It will work anywhere.
Even though there's
Outer space.
Even though there's no
Well, you have air groundings also. Okay. So what you have to do is have a metal plate of sufficient size. Now you see this in like oil storage tanks and water towers and a lot of things like that. Lightning loves to strike those things, and basically the reason it's hitting them is because they are earth grounded.
Okay. Well, what are some of the other questions that people ask you that you just that would be very easily explainable by this? One of the most common questions that people seem to have a problem with when creating your device or trying to understand why your device works.
A large number of people have tried to do it, and it didn't work for them. And of course, they can't be responsible for it. So I get called a lot of interesting names. And